Alright, there's a couple more things I'd like to say about log applications extending from the last lesson. First up, I want to talk a bit about populations and change of base of an exponential growth pattern. Populations are often referenced by yearly growth, which would be represented by 1 plus a rate. However, populations can be described based on doubling, that they double in a certain time interval, or triple, or experience 5-fold increase, or other things. These would be base 2, or 3, or 5, and so on. And we're talking about the same population, so there must be a way of making equivalence between these two things. So I want to look at that a little bit. Here's an example. It says if a population in Whoville increases by 2.5% yearly, write an equation for growth that's yearly. Pause and try that. That should be fairly straightforward for you to do. Alright, hopefully you got, now I used P for population. The population at some future time is based on an initial population times 1 to retain that population, plus the growth of 2.5% as a decimal raised to the time in years, which simplifies to a base of 1.025. And because that base is greater than 1, remember, that means growth. Now doubling. If I were writing doubling, then I should be able to say population is based on an initial population with a base of 2. And it's raised to the time. But clearly these can't be equal to each other. There's got to be some sort of a factor that we build in. So I'm going to put a k for a constant there, and k is called a proportionality constant. So it's the constant that would bring equality. Now because these are describing the same thing, I should be able to say that P naught times 1.025 to the t equals P naught times 2 to the kt. Pardon me. So we can see, if I divide by P naught, that this is independent of the population. Also, both of these are raised to the exponent t. So if I take the teeth root, pardon the dental joke, then this can be written as 1.025, and this can be written 2 to the k. That was a pretty bad joke, wasn't it? Now, I want to solve for that k. Because it's an unknown in the exponent, I'm going to use logs. So I'm going to write log of 1.025 equals k log 2. K log, that always makes me hungry for cereal. Oh, bad joke again. 1.025 divided by log 2. I guess it's time to turn on a calculator finally. And let's move that over here out of your way a little bit. Whoops. Bad calculator. Behave. Okay. And I'm going to turn it on, and I'm going to do log 1.025. I'm going to divide by log 2. And I'm going to get decimal 03562. Decimal 03562. Now, notice, by the way, that this is base 10. I could have used natural logs, which are a base e, and this should be equivalent if I change the base using a change of base rule. So, you know what I'm going to do? I'm going to be lazy and go second entry, and I'm just going to overtype the log with a ln. Oops. Come on back. There we are. And I'm going to make that ln. I guess I didn't save that much time. And I get the exact same value, 03562. Okay, so there's a little reinforcement of the idea of change of base, and that it was arbitrary to choose log base 10. I could have taken the natural log as well. Anyway, what I just found is this, that 2.5% growth is equivalent to doubling with a factor of 03562 exponent t. Now think about transformation of functions. T is the input. When I multiply an input by a small number, I get a horizontal expansion. So base 2 normally grows pretty fast compared to a base of 1.025, but if I horizontally expand base 2, it's going to stretch it out horizontally to make it like 2.5% growth. You could graph those, and we could see that they should be just like each other. 1.025 exponent x for input. The other one, 2 exponent bracket 0.03562 x. Now this isn't going to be perfectly equal because I rounded it after the 10,000th place. But if I make a window here and I say let's go from 0 to, oh, I don't know, 10, and let's go with zoom 0, and see what that looks like. It'll take a moment for the calculator to figure out the range to use. There's my growth of the 1.025 function, and the other function looks like it's not graphing, but it actually is. It's right on top of it. Just to prove it to you, let me go back here and make that one bold, and let's regraph. Here's the base 1.025 representing pretty slow growth, and there's your base 2 with a horizontal expansion. Alright, you might want to pause and think about that and play with that a little bit and look back over the calculations that I just did. But I just brought in a little bit of transformations into this to get you thinking about changing bases. So what I want to say before I leave is that any base exponential can be written pardon me, as any other base exponential by a horizontal expansion or a horizontal compression, as the case may be, depending on which direction you're going and what you're trying to convert to what. Now, that's within the rules of exponential bases, which have to be positive and can't be 1. All right, I want to talk about e and natural logs a little bit. People tend not to like this very much. E is a much maligned number. It's just like pi. It's irrational. It's a decimal that doesn't repeat and doesn't stop. And here's a build-up of what e is represented by. So you know about compounding. If I have growth, that's the 1, or the plus rather. So if I have 1 plus, and I take 1 divide by various values and raise it to an exponent for a year, and if n were 1, so compounding once in a year, this would represent doubling my money. If I compounded quarterly, I'd break the interest in 4 parts and I'd calculate 4 times, and I get a bit of gain. If I go to monthly, I get a little bit more gain. Daily, hourly, and so on. But you'll notice that between these, the change is less significant each time. This one looks like it's about, what, decimal 1/7. See how the change is slowing down, maybe we could say? This one, it looks like it's about 1046 or something like that, if I've done that right. This one is only decimal 0035. It's not changing by that much anymore. If I go from hourly to by the minute or the second or the nanosecond or whatever, pardon me, what you find out is that 2 increases, but the increase is gradually less and less, and this behavior is asymptotic. It's heading toward a number. If I let n approach infinity, the kind of growth that I'm representing is a continuous growth, constantly growing. Now n here, represented by infinitely large numbers, results in the value e. And we can see this graphically and play with this on our calculator if you want. Let's have a look at that. Let's just clear what we did a moment ago. Let's put this function in 1 plus 1 divided by input. So that's representing n, exponent n. Now, if I chose a window of inputs, remember we're trying to get pretty big here. So let's see, how big did we get? This was in the order of 1, 2, 3, 4, 5, 6, 30 million, right? So if I went to, oh, I don't know, let's go to 25 million. 1, 2, 3, 1, 2, 3, and let's scale by, oh, how about 5 million? Great. And for y, let's have a minimum value of 1, sure, and a maximum of 3, and let's scale by 1. Let's see what this looks like graphically. Hopefully I picked those okay. Oh, I didn't pick them that well. I'm going to go back and I'm going to change my domain. I think I chose something a little bit too big for us to see the effects. Let's go to something like 1,000 first of all. I should have checked this before I did this on the video. Oh well, my bad. Let's go from 0 to 1,000. Now, there you see there's a bit of curvature there, but quite quickly it's heading up to some value. I'm going to back this off even a little bit further, and let's just go to 100, and let's scale by 10 horizontally. Now we see a little bit more of the curvature happening. I guess I should have started there. Now, for comparison, I'm going to make y2 equal to e. And let's look. Aha! Asymptotic at that place, right? So, let's capture that and add it to our notes here. Make it a little bit bigger. This is y equals e. And I'm going to write asymptotic down here. Okay. So, let me just do an example of this to represent continuous growth. Pardon me. Base of e now, not 1 plus something. R is where you put the growth rate in as a decimal, and A and A naught are same as before. So, here's a question. How long does it take to double your money at 10% compounded continuously? Pause the video, try the problem, see how you do. Okay, hopefully you set up the equation to look like this. Doubling your money means the future value compared to the present value is 2. It's independent of what the beginning value is. So I could have $1 become 2. I could have $1 million become 2 million. The result is that that ratio is 2 to 1. So I can write 2 equals e, decimal 1 representing 10%, compounded continuously. Now, I have an unknown in the exponent, so I'm going to use logs. Because I see e, I'm going to use a natural log. So I'm going to use the power rule here, and I'm just going to write, as an aside, ln e equals 1, in the same way as log 10 equals 1. So ln 2 equals 0.1 t, t equals ln 2 divided by 0.1, or 10 ln 2, or ln of 2 exponent 10, and I guess we can turn on a calculator. I've had enough fun now. Let's go here. We have ln 2 exponent 10, close bracket, 6.93. 6.93 years is the value of t to double our money. There you go. That's it for application.